Okay, so if you're having to watch this from home, conservation of momentum, we have to, when we're talking about momentum conservation, we have to define a system. So let's take a moment and describe what we mean by a system of objects. So up until now, we've only really considered individual objects, objects that we would treat just by themselves. Now what we're going to do is we're going to look at a system of two or more objects. In this case, we're looking at the cue ball. And anyone here play billiards? You know what the red ball is? It's a solid, so it's going to be a number 1 through 7, and that one would be the 3 ball. So the cue ball is striking the 3 ball here during this collision. Now the leftmost diagram is showing the cue ball moving. You can probably see that because of the blurry action. The contact occurs right here. So Jack, like you mentioned, collision force. The collision occurs in the middle diagram. Now afterwards, can you tell by looking at the diagram that the red ball is the one that's moving and the white ball has sort of almost stopped its motion? Now below there's a data table, and I'm not so concerned about the data table just yet, showing you what happens to those speeds. What I'd like to do is I'd like to consider what happens during this portion right here. So I want to focus in on the contact forces that occur during that collision. Now, do you guys agree you're looking at it from top view? Which way does the gravitational force act? If you're thinking of this as a top view, you're looking at it from the top. Which way does gravity act? You guys agree? Into the board? Which way does the normal force act? Out of the board. We're not even going to try to draw those. If it were a side view, we'd draw those, but we're looking at it from a top view. So the only forces I'm interested in is the collision force between the cue ball and the red ball. So on this thing here, let's draw an arrow on the red ball that shows the collision force from the cue ball. And so if I were to look at just the cue ball alone, or the red ball alone, I would draw that force and say that's the collision force from the cue ball. I might say that's the force of the cue ball on the 3 ball. Cue in this case is spelled C-U-E, right? So I'm using C for the cue ball. Strikes the 3 ball, driving it to the right. We know the force is needed to change motion. So that red ball is going to take on some motion from the collision. Now, if I consider just the red ball, then yeah, but the red ball also exerts a force back on the cue ball. So if I drew that force up there to show the collision force from the cue on the red, could you draw the 3rd ball pair that shows how the red ball exerts a force back on the cue ball? How big would you draw it? Has to be the same. So since this thing is sort of centered here, right, I got those things in the middle, and I drew that one from the center out to the end. This one here should be here all the way to the end of that. And so this would be the force not of the cue on the 3, but the 3 on the cue. You can see that they're equal in size, opposite direction. If I consider them individually, we would see each object changes their motion. But when I look at them as a system, so when I look at them combined, I notice that it's sort of like me throwing a ball, but not letting the ball go. I see those forces sort of cancel each other. So since F3C is equal but opposite to FC, since those are equal but opposite, what we see is no total force acting. The total force is 0. When I combine them together, they're equal but opposite in size, which means the total force cancels, reduces to 0. Now what that does is it allows us to look at the momentum of these objects, which is their mass times velocity, is being conserved. The data table shows that one of the conservation laws, even though each one changes their momentum during the collision, the cue ball speeds up, or the 3 ball speeds up, the cue ball slows down, the total momentum of the system, so the combined momentum, remains unchanged, or what we'd say is conserved. So the total momentum stays the same. Now I'm going to put some numbers in here. I want to go in and look at what these values are on the data table. And again, this is from a different textbook, one that's a little bit more mathematical than the one that we would use. But if this is before the collision, the cue ball is coming in with a certain mass and a certain velocity, I'd multiply these two numbers together, right? So mass times velocity would give me 0.72. Now I noticed before the collision, the the 3 ball wasn't moving at all, so its momentum is 0. After the collision, for some reason, we have an ability to measure that speed there. We see that its speed slowed down quite a bit, from 4.5 down to 0.11. If I multiply these two numbers together, I get 0.018. And again, you need to use a calculator to go through and do that. But I definitely noticed the momentum of the cue ball became smaller. It became smaller by about 0.7 kilogram meters per second. It was 0.72, now it's about 0.02. So it decreased its momentum by about 0.7. Now, if I look at the, if I look at the 3 ball, I notice that it was at rest and now it's moving at that speed. Afterwards, if I look at its momentum, it's about 0.7. And the idea there is that the total momentum of the system stayed the same. Yeah, so this number, thank you, how I would get this, if I multiply these two numbers together, this is mass, that's velocity, that would be momentum. And so how I'm getting that 0.7 is I just simply take their mass and their velocities and combine them, okay, as a product. Now what I'm trying to show with this is that 0.72, so 0.72 is what I started with. Okay, can't write it right there. I'm going to write it down here. 0.72 is what I started with, turned into 0.02 plus 0.7. And so the idea there is that what I started with was 0.72, what I ended with was 0.72. Each object changed their momentum some, but the total remained the same. And so that's an idea of what we mean by conservation loss. So what I start with is what I end with. Now, the system has to be isolated. When I say a system is isolated, that means only the forces of impact, the collision forces, are the things that we care about. Any other forces are minimal compared to the collision forces, and so we say that it's an isolated system. The other thing that must be true is that it's got to be closed, which means that the mass doesn't change for that system, so we don't have any matter coming in or leaving. Now I'm going to test your hearing really quick, and this has to do with that bunching slack idea. So I'm going to freeze the frame, and I'm going to ask you to tell me what you're hearing. I have 5 different things, just as a little bit of a game. And then the last one is one that I want to tell me if you can hear what's going on here. Okay, so close your, I'm going to freeze this. Turn and tell that person that you're sitting next to what you're hearing here. That's a commercial, don't do it. Okay, there's another commercial, sorry. Okay, here they go. Can you tell that person that you're sitting next to what are you hearing? You guys get a phone? Okay, what do you get for this one? What'd you hear? What was it? What was the question? All right. Next one. Okay, what do you hear? Turn and tell. Okay, but what kind of owl? Yeah, I don't know. Whatever that one. All right, and how many people are 3 for 3 so far? You got all 3? All right, we're going to do 2 more. Turn and tell them. Yeah, you heard it. It is a clicking pen. 444, raise your hand. A few people. All right, last one. What is it? A plate smashing. All right. How many people 5 for 5? You got them all? Oh my gosh, I didn't know this going. What is that? Yeah, that one is actually a vacuum cleaner. Let's close that. All right. Now, the one that I really wanted to test is this one here. So this one I'm definitely going to freeze the frame, and you guys can't see this. So this one, tell that person that you're sitting next to what you hear. What did you hear? It's obviously a train, yes. But what else did you hear? What was that train doing? How can you tell it's speeding up? Yeah, what was it about that was telling you that it was speeding up? Okay, so a lot of times people hear they think what they're hearing is revolutions. Really, what they're hearing. Anyone ever hear you live near a set of train tracks where cars or trains are coming in or leaving, like the train station? Okay, I grew up in an area where trains were constantly coming in and then leaving that train station, and every time they come in or every time they leave, I hear this racket, this noise. What that noise is has to do with this thing called bunching slack, right? So that last question on your finger. What these things have are flexible couplings. And the idea behind that is that the engine of that car, of that train, cannot start 120 train cars all at once. It just simply can't do it. There's not enough torque in this case to be able to start everything at the same time. So what it does is it'll back up a little bit and make sure that every one of those couplings are not fully engaged. The couplings are like this, right? So if you think of the couplings like so, this would be disengaged, and then as the train car, the engine starts to move forward, it's going to use its momentum to start the next car. So that first clink that you hear is a transfer of momentum from the engine to the second car. Then it takes the two cars that are moving, and it uses that momentum to start the third car. So every time you hear this, that clank that's there is because the engine just simply can't start everything at once. So it uses the conservation of momentum to go do that. And so the same thing happens in reverse when it comes into the station. It can't brake it all at once. So same idea, all of those couplings are fully engaged like that, and then as it slows down, you're going to hear the clanking going in reverse. And so it's a pretty annoying sound. But that's the reason for it. So the bunching slack question down here, if you didn't get it, it has to do with momentum. They're trying to use the momentum of the engine to start the other cars, right? So if you didn't get that one, it's always a little bit tricky. That's what that answer should have been, okay? Other people had some version of that, like close to that. Okay, it's a momentum idea. It's using the momentum of that engine. Okay, now folks, what I want to do today is I want to show you, first show you where this derivation comes from. Now, I don't know why Newton's third law exists. I don't know why, but I do know why the conservation of momentum exists based on Newton's third law. If we take third law to be a true statement, then we can use the third law and the impulse momentum theorem to show that momentum is conserved. The idea behind this is that Newton's third law is pretty key here, that forces always come in pairs that are equal and opposite in size, opposite in direction. When the beige car hits the green car, and you guys can't see that on your things there because they're not color coded, but when the beige car hits the green car, it delivers an impulse. This portion right here would represent the impulse delivered. And that would be the impulse delivered to the green car. So that'd be the car on the right. Now, usually contact forces are not easy to describe. They're highly variable. They reach a peak value when things get maximally compressed, and then as they start to come off each other, the force reduces. So technically, that would be something called an area underneath that curve. If you've been in some advanced math classes, you might have learned techniques for determining areas underneath curves. I'll show you guys how to do that in our next unit using just a graphical approach. It's a very convenient way of determining what happens when forces are highly variable like that. Well, if that's the impulse delivered to the green car, this one here must be the impulse delivered to the beige car. If you're watching this from home, then you can see the colors there because the colors will show up on the video. But for you guys, it'd be the car on the left. Now, if I look at them individually, I would see that each one experiences an impulse. But when I look at them as a system, by the way, the area underneath that represents impulse. When I look at them as a system, what I see is the total area is 0. What that means is that the total impulse delivered to that system is 0. Now, this goes to the impulse momentum theorem. Impulse momentum says that F times T is equal to M delta V. So if the total moment or total impulse is 0, then what that means is the total change in momentum must be 0. So even though each one would experience its own change individually, when I look at them as a collection, I see there's no change to the system's momentum. The total momentum stays the same. Now, as an equation, oftentimes we say that we're going to try to take these ideas that are simple, but we have to try to put them into a language that we can use then to describe what's happening. So we would write this then as an equation. So equations are just very concise statements of laws. And so let's go ahead and write that the way that we would see this on an equation sheet. Symbology, that thing on the left is saying the sum of the momentum initially. So it's Greek letter sigma for summation. P represents momentum, and it could be a collection of objects. In this case, the 2 cars. In the previous example, it was the 2 billiard balls. Whatever I start with is what I end with. That whatever momentum I have to begin with, the momentum afterwards has to be the same. Now, below this, and I think you guys have some space there, I'm gonna put some numbers up here just to show you that in theory the math is really simple. In theory, it's really simple. The left-hand side could represent the momentum of the system before the collision. So I'm just going to give that 8 units. Now, I'm not going to use kilogram meters per second of momentum. I'm just going to say it's 8 units of momentum. After the collision, I have to have a total of 8. Let me just give you some numbers. Let's say that the cue ball came in with 8 units of momentum, and then it continued on after the collision with 2 units. Could you tell me how much the red ball has to have acquired? This is a sum, not a product. So it'd be 6 units. When I'm done, if I started with 8, I'd have to end with 8. What if the cue ball came in with 8 units of momentum, and when it hit and it continued moving because it had so much mass that it continued moving with 5 units. The other one has to have had, but now it must have 3 units. So the idea in theory is really simple. It's just whatever I start with is what I end with. The tricky part is that momentum is a vector. And you might remember that when 2 cars are going in the same direction, their momentum is reduced when their velocities are same direction, but when they're in opposite directions, their relative velocities are quite larger. If I have 8 units come in, and it's such that this one rebounds with a velocity or with a momentum of, let's say, 2 units in the opposite direction. So do you understand the idea that it's coming in this way, and it hits and it bounces back? What must be the momentum of the other one to still have 8? It has to be 10. And this can sometimes cause a little bit of confusion. And it has to do with the fact that those things are directional quantities. So 8 could turn into -2 and 10, and so I still get a total of 8 afterwards. This one can be a little bit challenging to fully get, but these other ones, it's just an addition problem, okay? Now, when we look at collisions and we look at conservation of momentum, there are three scenarios that we typically consider. These three scenarios are the ones that we have to develop equations for to be able to describe. Probably the most challenging part of this course, this unit at this point, is going to be using conservation of momentum equations. There are three scenarios that we would typically consider. I'm using the term hit and stick. A very common example of that are football players that hit and collide, and they sort of move collectively together. Objects hit, combine, and then they move afterwards. The basic form of this equation, and again, I want to show that each one of these things here starts with this as an equation. That's the central idea that says momentum of the system before is the same as the momentum afterwards. How we would typically look at a hit and stick problem is we have some object A colliding with another object B. During that collision, the only forces that I really care about are the impulse forces during that collision. So I'm going to say impulse occurs when they hit. Afterwards, what we see is that these two objects are sort of stuck together. Sometimes they even change their shape a little bit because they sort of like melded together. So A and B sort of move collectively. Afterwards, they move with a smaller final velocity. So I might even put little initials and finals on there to say that one object comes in, collides with another object, and then they move collectively afterwards with the same momentum. Now, how I'm going to write that as an equation. You'll see that there's like three forms of the equations that we would use. This one here would look like this. MAVA initial represents the momentum of that first ball or the first object coming in. That's take their mass, take their velocity, multiply them together. After the impulses are delivered, we see that both objects now move collectively with the same velocity. So we would combine their masses. We would say MA adds to MB. Because they're going to move as a collective unit. Of course, then they move with a smaller final velocity. So VF would end up being smaller. And that's because I have more matter moving, would have to be moving slower to be able to have the same momentum. So that would be the general form of that equation. If we had two objects hitting and sticking together, that momentum becomes that momentum, they have to be equal. Now, I'm not going to do any numerical problems with you guys today. We're going to save that for tomorrow. What I want to do is I want to show you the three general forms up here, and this one takes a little bit more space. Okay, so if I had hit and rebounds, where the cue ball coming in and hitting the red ball, and they sort of move separately afterwards, the basic picture would look something like this. Let me use a different color. There's some sort of impulse that's delivered. And afterwards, A and B move separately. This is probably the most complicated of the three different kinds of scenarios we could look at, because we could have more terms than just this here. So if I were to go write the equations for this, that portion would represent the momentum before any collision occurred. Well, after the collision, because the objects could be moving separately, each object could have its own momentum afterwards, so I just have to take their masses and multiply them by their respective velocities. that could be the set of equations that we would use for describing a hit and rebound, where objects hit and bounce off each other. And then the last one is an explosion idea. And explosions are common in maybe athletics, where two objects are sort of pushing off each other. It could be really common in like chemical explosions, when things sort of explode apart from an internal force, that things split apart like that. For this one, the general form would look something like this, where these objects are sort of combined together to begin with. They push off each other. When they push off, they each deliver impulses equal and opposite to each other. And then when we're done, what we see is A and B separate with equal but opposite momentum. So their velocities would sort of be in opposite directions. Mass matters here. So whichever one is more massive is going to be moving slower than the other one, to show that their momentum would be the same. The general form for that equation sometimes we'll put absolute values around those to show that if one is -3, the other one is 3. Okay, so again, it's just an absolute value thing. Those are the general forms.
What's the next?
Sorry, I know the handwriting's not the best. I wish I could do that better. Especially for people that are home that can't ask these questions. Let me try it with the pen. Better? Okay. Sorry. Folks, again, this is a little bit more mathematical. I don't want to do any of the problems with you guys today, just simply because I think I've sort of extended or expanded, exhausted our time right now. So we're getting really close to the end of the hour. I'd like to stop the video here, but I'd like to show you these collisions up here with these dynamics cards. It gives us a chance to get out of our seats for a few minutes. You can pack yourself up. You can do all that kind of stuff. That's fine. But I would like to showcase the ideas of what we talked about there with an actual visual. So take a minute, get yourself packed up, then come around to this table for a few. That would be preferred.